Hi, Algebra 1. Welcome to week 7. So in this week, we're going to talk about special factoring patterns, and we're also going to talk about higher degree polynomials. So the first one is the perfect square trinomial pattern. So you might have been seeing this in the IXLs and seen this pattern, but this is one that's definitely going to be helpful for us. So what ends up happening is that the first number and the second number ends up being perfect squares. So you see how 9 is a perfect square and 4 is a perfect square? So that should kind of cue you into this being a special factoring pattern. So 9 squared is 3, so that's 3 squared. 2 squared is 4, okay? So what the middle ends up being is the middle ends up being twice the numbers that are being squared, 3 times 2. Well, that's 2 times 3, which is 6, times 2, which gives you the 12x. So that checks out. So what this pattern becomes is your first number with the x, so 3x, and then since they're all pluses, plus 2. Okay, and that would be your answer squared. And you can check that by multiplying. So for here, I see my 2 perfect squares there. So this is going to be 7 squared and this is 6 squared, and I have to check the middle. So 2 times 7 times 6 does give me 84. So the only change for this one is this one's going to be a minus in between. And that would be my answer. And like I said, you can always check by double distributing or foiling. So how do you know the given problem is a perfect square trinomial? So you definitely want to check that the a and the c, so the first and the last terms are perfect squares, because remember the form is ax squared plus bx plus c. So a and c have to be perfect squares, and then that b should be twice the product of a and c. Okay, so that is what the b term should be. It should be twice the product there in the middle. So here's our first example. So this is 9 squared, and this is 5 squared. So I have to check the middle. Is this 2 times 9 times 5? Yes, it is. So this is going to give me 9x plus, and it's a plus because it's addition all throughout, 9x plus 5 squared. Looking at the next one, I see a subtraction, so that's going to tell me right away this is going to be a minus in between. Only thing is, though, I don't see any perfect squares here. Okay, I don't see any perfect squares with the 12 and the 363, which probably means I have some sort of GCF to pull out. And that GCF is a 3, so I can divide all these by 3 and put a 3 on the outside. That's going to give me 4x squared, and then minus 44x plus 121. And then now I have the perfect squared, because this is 2 squared and this is 11 squared. And this is 2 times 2 times 11. Yep, that checks out. So this is going to be 3 on the outside. Since it's a minus, it's going to be 2x minus 11 squared. So that's what we have there. All right, solving. So we're going to set these equal to 0, factor out a GCF, and then solve these. So setting these equal to 0, I'm going to add over the x to the other side. All right, so this is going to give me 4x cubed minus 4x squared plus x equals 0. So right away I have a GCF here. My GCF is an x. I'm left with 4x squared minus 4x plus 1. I do have perfect squares with my a and my c terms. So this is 2 squared and this is 1 squared. And the middle has to be 2 times 2 times 1, which it is, so it checks out. So factoring this is x on the outside. Since there's a subtraction here, I'm going to have a minus, so it's going to be 2x minus 1 squared. All right, looking at the next one, so I got to move a whole bunch of stuff around. So I've got to subtract the x squared, which gives me a 9x squared, which means I'm probably going, my a term is a perfect square, so it's probably going to be some sort of special factoring pattern. I'm going to add over the 30x, so plus 30x, and then I'm going to subtract over the 20, which is going to give me a positive 25 equals 0. And then I have here, this is 3 squared, this is 5 squared, this is 2 times 3 times 5. Yep, it checks out. So my pattern is 3x. Since it's all pluses, it's going to be 3x plus 5 squared equals 0. So the one thing I did, and I did this on purpose, is you can't leave your answers like this. So it's actually still equal to 0. So for here, this is still equal to 0. So I still have to find my answers for x. So I actually wasn't even done number 3. So for number 3, I have to write it out, double, and I have to find out what x is equal to. So I'm going to set all of these equal to 0. So I end up getting a double root, which we talked about in an earlier video. So x is going to be equal to 0, positive 1/2, because I'm going to add over 1 and divide by 2, and positive 1/2. So that's my final answer. Where for here, if I write it twice, I'm going to get another double root. And remember, a double root is when that vertex of that U shape touches the x-axis, and you'll learn more about that in algebra. So I'm going to set these equal to 0, equal to 0. I'm going to get negative 5/3 and negative 5/3. And yes, I do want you to write it twice. Okay? All right, for the next section, we're going to go through, these are higher degree polynomials, okay? So these are like x to the 4th, x to the 6th, and so on, okay? They can even go up. It could be x to the 8th, and so on. So looking at the first one, since it's a binomial, it makes me think difference of 2 squares, and it is difference of 2 squares here. This is 9 squared, and this is actually x squared, because you would multiply those together. So if I'm going to write this out, x squared plus 9, x squared minus 9. However, I have another difference of 2 squares here. This is x being squared, this is 3 being squared. So this is x plus 3, x minus 3, and this is x squared plus 9. And that's my final answer. So a lot of, kind of like when we were doing factoring by grouping, a lot of these higher order polynomials, especially if they're binomials, they might have a difference of squares there at the end. So you might end up factoring twice. So looking at the next one, so this is going to be 5 squared and x squared, all squared, x squared squared if you want to write it like that. And then this is going to be 3 squared. So it's going to be 5x squared plus 3, 5x squared minus 3. And that's going to be my answer. And you can always check that you have the correct answer, the correct exponent, just by quickly multiplying. So if I multiply 5x squared times 5x squared, it gives me 25x to the 4th. Okay, so when you multiply, you add the exponents. So that checks out. And you can continue going on. So 5x squared times negative 3 is negative 15x squared, positive 15x squared, and a minus 9. These cancels in the middle, and I end up getting the same as the original problem. All right, looking at the next one. Okay, this is interesting. This comes up a lot where you might have different variables for your first and second one. So this is going to be 4 squared, and this is x squared, and y squared, So this is going to be 4x squared plus y squared and 4x squared minus y squared. So this once again is a difference of 2 squares. This is also a difference of 2 squares. So this is 2x all being squared, and this is y being squared. So I'm going to leave the 4x squared plus y squared, and then this is 2x plus y and 2x minus y. So that was a real tricky one. Looking at the next one, I've got to the 6th power. So this once again is a difference of 2 squares. This is 7 squared, and this is actually x cubed squared because you have to multiply the exponents. 3 times 2 gives you 6, and this is 1 squared. So to break this down, this is going to be 7x cubed plus 1, 7x cubed minus 1. And then once again, you can check by multiplying. So multiply those together, it gives me 49, add the exponents, x to the 6. So it kind of checks out there. All right, let's move on to trinomials. So trinomials, in this case, I don't have a leading coefficient in front of there, so I can use add multiply. So I need two numbers that multiply to 25 and add to 10. So those two numbers are going to be 5 and 5. But when you write your exponent, you have to increase it so it's x squared, because an x squared times an x squared is going to give you x to the fourth. So that's kind of the interesting part about trinomials. You can factor them exactly the same, you just need to increase your exponent. So this was an easy trinomial because it was just add multiply. I didn't have to use the British method. Whereas this trinomial is going to be the same thing. First thing I have to do is I have to factor out a 12. That's my GCF. Actually, before I do that, you can also write your answer like this. X squared plus 5 squared. Okay, you're more than welcome to write your answer either way. All right, divide everything by 12. So 12 goes on the outside. Then I get x to the fourth plus x squared minus 2. So I need two numbers that add to 1 but multiply to negative 2. So negative 2, and that would be what? 2 and negative 1. So that means the 12 is going to go on the outside, and this is going to be x squared plus 2, x squared minus 1. All right, because the x squared times the x squared, like before, the x squared times the x squared is going to give me the x to the fourth. All right, another one here. So divide by the GCF, which is a 3. So a 3 goes on the outside. And then I'm left with x to the sixth minus 2x cubed minus 3. Another add multiply. So two numbers that add to negative 2 and multiply to negative 3. That's going to give us negative 3 and 1. So the 3 stays on the outside. This is x cubed minus 3 and x cubed plus 1. Because when you multiply, the cube times the cubed is going to give us x to the sixth. This one, I don't have a GCF, so this one you're going to have to use the British method. So when you multiply, it's going to be 3 times 6, which is 18. I need two numbers that multiply to 18 and add to 11, 9 and 2. When you plug them in, it's 9x squared plus 2x squared, because there's an x squared term in the middle. Okay, so it's not just an x term, it's an x squared term. So make sure that you plug those in. And then I have the 3x to the fourth plus 6. Now I can go through all of the grouping. So I'm going to group the first two, group the second two, factor out a GCF of 3x squared gives me x squared plus 3. Factor out a 2 gives me an x squared plus 3. This factors into x squared plus 3 and 3x squared plus 2. So similar process, even when you're taking out the GCFs and everything with the British method, the factoring by grouping, you're still going to end up getting an x squared answer. And once again, you can check it. X squared times x squared is going to give you x to the fourth. Moving on. Here are our steps of factoring. So I've been kind of repeating these over and over and over again, but I wanted to give you a flow chart with it. So the first thing you always want to do is you want to make sure that you're factoring out a GCF. That should be your first step. Next thing, it's all going to be based on the number of terms. If you have 2 terms, it's going to be the difference of squares. If you have 3 terms, you have options. It might be, so that's your trinomial, it might be a perfect square trinomial. So check that the A and the B are the squares, okay, that they're perfect squares. Or maybe it's an easy one. So if you don't have a number here with your A value, then it's just add multiply. Okay, add multiply. If you do have an A number there, then you need to make sure that you use the British method. Last thing you want to ask yourself is, did you factor completely? Meaning, are there any hidden difference of squares? Okay, check for those. Any hidden difference of squares that we have there. All right, well, I'll see you guys all in our live chat.